Hello, everyone. A very good evening to all of you. Let's start with our third session on science and technology. I'm sorry that I could not take the classes on Thursday and Friday because there was something, a kind of medical emergency at my home that I'm going through, because of which I have been a bit irregular. But I'll try my best to be as regular as possible in the coming sessions. So, first and foremost, if I'm audible and visible, please give me a thumbs up if it's all good. Great, wonderful. So let's begin. So we had started our chapter of energy, and in chapter of energy, we had completed some portions of energy. First, we completed all the things related to non-renewable sources of energy, where we discussed about coal, petroleum, and some of the other sources. And then in renewable energy, we had a discussion on solar energy, on wind energy, on geothermal energy, and then we had started on biofuels. And in biofuels, we had done certain discussions. For example, we understood what are the various generations of biofuels. And then we had a discussion on bioethanol and biodiesel. So these are the things that we have studied. Going forward, what we are going to discuss in today's class is largely related to biogas. First, we'll understand what is biogas. And then after that, various different aspects of biofuels, India's biofuel policy, and some of the issues related to biofuels. So these are the things that we are going to discuss in today's class. And then once we finish off this portion of biofuels, the next portion that we are going to discuss is nuclear energy. So that is what we have in store after this. All right. So let's begin first with the basic understanding of what do we mean by biogas. Now, in case of biogas, what we understand is that biogas is the gaseous form of biofuel. The other two forms, like biodiesel and bioethanol, they are the liquid forms. Now, in case of biogas, typically we are saying that this is a gas which is produced by the breakdown of organic matter in the absence of oxygen. All right, breakdown of organic matter. Now, when we say organic matter, and organic is a term that I have used in the previous class as well. Can you first tell me what do you mean by organic? When I say organic, what is the meaning of organic? Hmm. So some saying natural, living source, bio-based, made from remains of plants and animals, biodegradable, plants and animals. Okay, let me flip the question. Can you tell me element, one element which will definitely be present in anything that is organic? What is that one element that will always be present in anything that we call as organic? Yes, Ankit, you are correct. Tirtha, you are correct. Aditya, almost correct. Shimna, correct. Rishu, correct. Shweta, correct. Abhinav, correct. Babulkar, great. So a lot of you have been giving the correct answer. So anything, when we call something as organic, it would definitely contain carbon. All right, it definitely has carbon in it, and that's why when we say that there is any compound which is an organic compound, it means that that compound definitely has carbon in it. And that's why any organic matter, so organic matter, largely we are saying that these are carbon based. These are carbon based, largely you can say plants and animals. So organic. Now, when we say biogas is typically a gas produced by the breakdown of organic matter in the absence of oxygen, in this case, what we basically get is largely based out of methane. So if you see this diagram, this is how the production of biogas happens. That you take the leftovers, you take the organic waste. It can be cow dung, it can be animal waste, it can be plant based waste, it can be agricultural waste. So there can be all these wastes, and we then take it to something called as an anaerobic digester. Anaerobic means what? I'm sure many of you know this. Anaerobic means absence of oxygen, right? Anaerobic means absence of oxygen. Just give me one moment, please. Sorry, if please let me know if audio video both are working fine for everyone. I see a couple of complaints, that's why I'm asking. It's all good. All right. So anaerobic means what? Absence of oxygen. So when we say anaerobic digester, it means that we are talking about a kind of a plant that you have made which has limited supply, or we have cut off this oxygen supply. Now, when the decomposition happens in the absence of oxygen, this is where we see that some gases will be emitted from here. All right, some gases will be emitted, and these gases that we are getting from here, this is the biogas. All right, this is the biogas. So that's why we are saying that we get biogas by the decomposition of organic matter in the absence of oxygen, right? So, and then the biogas that we get, it can be used in various ways. It can be used for cooking, it can be used for electricity generation, it can be used for various different things. So this is how we get biogas. Now again, remember that when it comes to biogas, most importantly, it has methane. Most importantly, it has methane. And apart from methane, there can be some of the other gases as well. For example, carbon dioxide, hydrogen sulfide, even traces of oxygen, nitrogen, water vapor. All these things can also be mixed, but largely it is methane. Up to 75%. Up to 75% is just methane. And then apart from that, the other 25% could be the mix of all the other gases. So this is what biogas is. Now, biogas, that's why it can be used in various different ways. When it comes to biogas, one of the most important advantages of biogas, and of course there are many advantages very similar to what we discussed for some of the other renewable energy sources as well. Does not pollute, it's a renewable energy source. So there are all those things which are, you can say, more or less self-explanatory. But apart from that, there is one very, very important application of biogas that we must understand. And this is how they can help in reducing global climate change. Why are they important from this perspective? That they can offset some amount of greenhouse gas emission. Understand this. That why am I saying this? Now, usually, for example, let's say if we are using cow dung, right? We are using cow dung, or let's say any animal waste for biogas generation. Now, even if cow dung is just left without doing anything, or without trying to use it in a biogas plant, etc., the cow dung will still decompose. Correct, it will still decompose. You might have seen it, that if cow dung is lying on the sides of the road or somewhere in the fields, within a week's time you might see that it starts to get decomposed, and it just decomposes altogether. Have you seen it? You might have seen it. Yes. Yeah. So doesn't mean that you now go and start staring, but I'm very sure that most of you have observed this. So now in this particular scenario, when it comes to this natural decomposition, this natural decomposition emits methane. All right, it would lead to the emission of methane via this process of decomposition. But when we are using this to create biogas, now you might say that okay, biogas also has methane, so where's the difference? The difference is that now you are doing the combustion of this methane, you are burning this methane, and with this combustion of methane, it oxidizes. Just understand this. It oxidizes, very similar to what we had discussed in methane hydrates. It oxidizes, so what you are releasing is actually carbon dioxide. So, in case of natural decomposition, all right, in case of natural decomposition, in case of natural decomposition, we would see emission of methane. Natural decomposition, we might see emission of methane. But when it is converted to biogas, when it is converted to biogas, then carbon dioxide emission happens. Now, if you remember, we discussed this, that compared to carbon dioxide, methane is a way more potent greenhouse gas. It can be 25 to 80 times more dangerous as compared to carbon dioxide. So that's why if we had an option between releasing carbon dioxide into the atmosphere versus releasing methane into the atmosphere, we would prefer releasing carbon dioxide instead of methane. Correct? So that's why this is something which is very, very crucial for us to understand. So that's why this is one very important advantage of using biogas, because it can at least offset some amount of greenhouse gas emission from the natural processes. And even nitrogen dioxide is one of the components which is there in the natural decomposition, which can be up to 300 times more uh, dangerous than carbon dioxide as a greenhouse gas. So that's why these are some of the advantages that we see with biogas. Now, coming to a very, very important topic from the perspective of biofuels, and this is the National Policy on Biofuels of 2018. Now, in 2018, the Government of India came out with a new biofuel policy. Now, was this the first biofuel policy? The answer is no. Before this, we had the 2009 biofuel policy as well. But the 2009 biofuel policy did not achieve a lot. And the kinds of targets that we had kept for 2009 biofuel policy, we were nowhere near achieving those targets at all. And that's why we see that there was an overhaul that was done in 2018, and that's why the Government of India came out with a new set of targets and new set of policy implementations with this new biofuel policy. Now, this new biofuel policy has been very, very important, and it has been doing a fairly good job in the context of adding our capacity of biofuels. Now, what have we done different this time? What was lacking in the 2009 policy versus what have we done better in the 2018 biofuel policy? The 2009 biofuel policy had, you can say, same kind of targets that 2018 biofuel policy also had, but the roadmap was not clear. The way we are going to achieve these targets were not clear, and that's why we see that 2009 biofuel policy could not achieve a lot. For example, 20% blending of ethanol in petrol and 5% blending of biodiesel in diesel was supposed to be achieved by 2017, according to the 2009 biofuel policy. So by 2017 we should have achieved these targets, but at by 2017 we had achieved only 4% of blending of ethanol in petrol. So imagine, target being 20% and we achieving just 4%. So we had done just, you can say, we had achieved 20% of the targets that we were supposed to get. So not even 50%, not even 60, 70%. So that is why the main reason what we see is that there was a lack of proper implementation rules, or there were lack of proper understanding of how exactly what should be the roadmap, how should we achieve these targets. Now this is where you can say that we learned and we came out with a clearer picture, with a clearer roadmap. How exactly? First, categorization. For the first time in 2018 biofuel policy, we see that we did a categorization into different generations. Remember, we discussed about the first, second, and third generations. So, this is what we did. We categorized biofuels into first, second, and third generations. Now, remember that there was no fourth generation, and as I discussed the other day also, that fourth generation is something which is more experimental in its approach. So now we did a categorization, first, second, and third generation of biofuels, and these are the same as we had discussed in the last class. Then the scope of raw material. Now, this was very, very important. We clearly defined that these are the raw material that we are going to use for biofuel production in India. What kind of raw material? First, sugar based. Sugar based meaning anything that has sugar content in it. So, for example, sugarcane juice. So, sugarcane juice can be used for biofuel production. Then after that, second is starch based. So starch based meaning that these are good sources of carbohydrates because starch is carbohydrate. So starch based where we have corn, for example. So these can be used for biofuel production. Then after that, agricultural waste. Agricultural waste. What kind of agricultural waste? Crop residue. After the the crop has been taken, the residue of the crop that is left in the field, that can be used as biofuel. Similarly, apart from that, there are other sources that can become agricultural waste and which can be used for biofuel production. So for example, in agricultural waste, broken rice, broken grains, uh, rotten potato, all these things were also mentioned. All right. So crop residue, broken grains, rotten potato, interestingly, has been mentioned. See, it's very simple that we don't want to use potato because potato is a staple crop for India. And everywhere in the country, potatoes are being consumed in one form or the other. So that's why potatoes, although they are very good sources of carbohydrates and hence they can become very good sources of biofuels also, yet they have been kept out. And that's why rotten potatoes have been mentioned. That potato which is unfit for consumption. Potatoes that might have gone to your samosas and dosas in the restaurants. So those kind of potatoes, instead of going into your food, will now go to biofuel trans. So that's why these all things were mentioned as agricultural waste. And apart from agricultural waste, we also see the scope for municipal waste. Municipal waste. The waste that we are generating in our homes, that can also be used. Then after that, what else? Surplus crops. Now, this is also very, very crucial because many times you might have seen this, you might have heard this, you might have read about this. That many times what happens is that for a farmer, let's say if because of some uh, weather pattern related reasons, the productivity has not been that great in any given year, then the farmer, of course, loses because the production is low, they are going to earn less out of it. But when the production is very high, what we call as bumper crops, in bumper crops when the production is very high, then also many a times the farmers suffer. Why? Because the production is very high. So because the demand is limited, supply is very high, the prices will fall. So that's why they don't get enough. They would have spent a lot in production, transportation, storage, etc. They're not getting enough from the market. So many times what happens is that farmers would just throw away the extra production. So this is where the government is saying that instead of throwing the extra production, this can be passed on to the government, so that government will use it for biofuel production, and the government would also pay the farmers for giving this surplus. So for a farmer, it also becomes a source for additional income. Correct? It becomes a source of additional income for them. So that also is very crucial point. So surplus crops, and then there is another very interesting point that has been mentioned, and this basically is used cooking oil. Used cooking oil. Now, this used cooking oil is also very interesting because you might know this, that if you reheat the edible oil multiple number of times, it's not good for your health. Correct? When you start reheating the oil, when you start reheating the oil, this is where a lot of fats that you have in your oil, they start to convert. The amount of saturated fat starts to increase, the amount of trans fats, they start to increase, and that's why it is not good for consumption anymore. So that's why, if let's say a certain edible oil has been heated beyond a certain temperature multiple number of times, then it is not fit for consumption, right? But do you ever go and ask in a restaurant this, that have you used an oil which is new? Are you reusing the oil? Are you reheating the oil? We don't care. We just go to the restaurant, we go, we eat a lot, and we come back. So that is where it is actually bad for our health. So this is something that also has been taken as a part of it, that used cooking oil can be, there will be agencies all across the district, and these agencies can buy the used cooking oil back, and this used cooking oil will then go to a biofuel production plant, rather a biodiesel production plant. So that's why in this particular scenario, this becomes very very crucial from the perspective of the raw material. So that's why, as you can see, that very importantly this time, the scope of raw material, that okay, these are the things that we can use as raw material for biofuel production, they have been completely defined. Then protection to farmers, and the protection basically is in terms of surplus, or what we call as bumper crops, that they will be protected, and they can sell the extra with the help of these parts of the policy. Then there is something called as viability gap funding. Now, the government of India also has kept a scope for viability gap funding in biofuel policy. Now, what do we mean by viability gap funding? So, when we say viability gap funding, meaning that if there is any gap in making a certain project viable or making a certain project work, so if financially, if there is any gap, so for example, let's say there is a certain initiative, there is a certain policy that needs 5,000 crore rupees, but as an allocation only 3,500 crore rupees has been given. So now there is a deficit of 1,500 crore rupees. So these 1,500 crore rupees will also be filled up by the government of India wherever they have kept the scope of viability gap funding. So that's why in this policy also, the scope for viability gap funding was actually kept by the government of India. And that's why it becomes very, very crucial from this perspective, that if there is any fund, any gap in the amount of money that is required for this project to work, that will be taken care of by the government of India, and that is what we mean by viability gap funding. This is what we mean by viability gap funding. So that's why scope for viability gap funding has been kept by the government of India. Now, lastly, what we see is boost to biodiesel production. Now, when it comes to boost to biodiesel production, we see that especially more emphasis is being given to biodiesel production in India, because we do understand that bioethanol production is easier as compared to biodiesel production. The productivity, the yield is higher in bioethanol. Uh, the crop availability, the raw material availability is way higher in case of bioethanol. So we see that there are all these things. So in that context, what we see is that biodiesel production needs extra help, and that is also where the scope has been kept alive for doing that. So this is basically what we see in terms of national biofuel policy, and that's why this brings in a lot of expected benefits. So, for example, reduced import dependency. Now, this is very, very crucial because what do we want? We want that we should be able to mix bioethanol with petrol and biodiesel with diesel. So once we start doing that, so when let's say when we are in a position where 20% blending of bioethanol with ethanol, bioethanol is being done with petrol, it means that instead of we importing 100 liters of petrol, even if we import 80 liters of petrol, that's enough. Understood this? That if right now we are importing 100 liters of petrol, once we start doing the blend where 20% bioethanol is being used, then you have to import only 80 liters of petrol. So when we have to do that, it means that it is reducing our import dependency. So this is very, very crucial, and we already see that it is going to make a positive change. So for example, 1 crore liters of E10 fuel saves rupees 28 crore in total, or of 28 crores of forex reserves. Now, this is very, very crucial. And now you might think that, okay, 1 crore liters is a huge number. No, it is not. Because in a year, very easily, more than 200 crore liters of production happens. So just imagine that if in 1 year, if there is 200 liters production of E10 fuel, it means that it 200 liters, 200 crore liters would save how much? 28 into 200, meaning a total of rupees 5600 crores worth of forex reserves will be saved in one single year. And when we say E10, E10 means that this is 10% blending. E10 means 10% blending. So we are aiming for 20% blending, which has already started in some of the districts in India. So this is how the nomenclature works. E10 meaning 10% blending, E20 meaning 20% blending. You will find these terms in your newspapers as well. E10, E20, E25, E80, E85, all these terms will be used. So just understand that when this term is being used, this is the meaning. E10 means 10% blending, E20 means 20% blending, and so on. So that's why reducing import dependency is one very, very crucial thing. Then cleaner environment. Of course, cleaner environment, because when it comes to, so for example, again, if we take the figures, 1 crore liters of E10 fuel will be able to reduce the carbon dioxide emission by 20,000 tons. All right, 20,000 tons lesser of carbon dioxide emission. So that's why these are huge figures that we need to understand. Then health benefits. So for example, lesser use of used cooking oil, correct? Lesser use of used cooking oil, or improvement in air quality. All these will be very crucial aspects of health benefits. Then municipal solid waste management, the municipal waste can be used. Then infrastructure investment in rural areas. Now, again, what we understand is that setting up of these biofuel plants can be done in various different parts of the country, correct? It's not necessary that you choose an urban area. We can choose a rural area and we can do the entire setup there. So for example, if we have one such plant which has a capacity of 100 kiloliters per day, so one such plant can bring in investment of up to rupees 800 cr. One such plant which has a capacity of 100 kiloliters per day will be able to bring in an investment of up to rupees 800 crores So in the rural areas, a lot of investment will happen, a lot of infrastructure improvements will happen. So, and it will also create a lot of opportunities for the people living in these areas, a lot of employment generation opportunities, which are not really dependent only on this plant. Because wherever a new plant is set up, an entire economy starts to develop all around that plant, right? So that's why it is going to bring in a lot of investment and a lot of opportunities for the people living in these areas. Then employment generation. Again, one such plant of 100 kiloliters per day will be able to easily employ up to 1200 people. It will be able to employ up to 1200 people. So that's why this is something which tells us about the kinds of opportunities that these kind of things can bring in. And additional income to the farmers, right? Additional income to the farmers in terms of the surplus produce, especially in terms of surplus produce, and the farmers who are involved in these kinds of crops from where it could be bought. So that's why we understand that it will bring in a lot of benefits, and it has started bringing in a lot of benefits altogether. So that's why we see that there are all these different aspects of the policy: additional income to the farmer, infrastructure and investment in rural areas, environmentally friendly fuel, then employment generation through biorefineries, etc., reduced import dependency, health benefits, waste to wealth, waste management. So there are all these kinds of improvements or advantages that we see out of this policy. And then we see that for especially for bioethanol production, we see that there is an additional outlay of rupees 1969.50 crores being given up to this financial year as a part of Pradhan Mantri Jeevan Yojana. So that's why we see that there are all these things that are being done in the context of biofuels. Now, one thing that we need to understand is some issues as well. That yes, it looks like that there are a lot of benefits, but at the same time, there are certain issues, and largely the dimension of food security and biofuels. Now, when it comes to biofuels, we do understand that most of the biofuels that we are using, it is coming from food crops. We discussed about the first generation, third generation, second generation, fourth generation, all these, but the reality of the day is that very easily you can say that up to 80% or more biofuel production happens from crops. It happens from food crops with the help of food crops. So what is happening is that a lot of these crops, which are also staple food for us, corn, oil seeds, potato, sugarcane, soya bean, all these are what? All these are crops which can also be used for biofuel production. Now, in this case, there are certain problems that start coming in. So, for example, it can lead to production of genetically modified crops. That we might see an encouragement of genetically modified crops where we are modifying the crops in a manner that they become more useful for us as a fuel rather than being useful as food. So we might want to enhance certain qualities in the crop so that they become more useful commercially rather than from the perspective of our consumption. So that's why this is a threat. Then there can be a decrease of food import capacity, especially for the poorest countries due to increase of prices. Now, what's happening here? In this scenario, the supply remains constant, correct? Supply remains constant, but the demand increases. Why is the demand increasing? Because something that was just a food crop until now has also become a crop useful for fuel. So that's why supply is constant, but demand is increasing. What does it do? Leads to price rise, correct? Similarly, it can cause increase of food prices due to increasing demand for agricultural produce. What's happening in this scenario? Food food supply will decrease. Supply basically, what happens to supply? supply decreases, the demand is constant. Why am I saying this? Because in this particular scenario, what we are seeing is that the supply for food, meaning that let's say if you were getting 100 kg of soybean, you are getting 80 kg of soybean because the other 20 kg is going for biofuel production. So that's why supply is decreasing, the demand is constant. The demand is there for both the food and the fuel. So again, it is a situation that leads to price rise. Then food and fuel crops, they compete for land and water resources and thus increasing their prices, because resource cost increases, the land cost, the fertilizer cost, the water cost, they all start increasing, and hence that also leads to price rise. So overall, that's why we might see that it will lead to a rise in the food prices, and we already have noticed an increase in the price rise. It's not only about inflation, but because of biofuels in the Europe, it has been seen that there has been an increase of 10 to 15%. 10 to 15% price rise has happened only because of biofuels and the consumption of these food crops in the biofuel production in Europe. So something similar can happen in India as well. So that's why we have to be very aware of these kind of situations. And this kind of demand might also lead to a lower food quality, that just want to we might just focus on the quantity, that we need to produce more. We might not think of what kind of nutritional value it has. We might not focus on what kind of nutrients does it have and is it healthy enough, and we just want to increase our productivity. So that also would lead to a situation where the quality of the food starts to decrease. And then lastly, water availability for human consumption will be threatened, because many of these are also crops which are very water intensive crops. They need a lot of water. Can you tell me two of the most important crops which need a lot of water, which need the most amount of water? So rice, sugarcane, at least. I mean, paddy and sugarcane, you can say. Yes, jute also has been mentioned, but yeah, jute is not one of the food crops here in this context. But sugarcane, rice, or paddy, we know that these consume huge amount of water, and both are crops which can actually be used for biofuel production as well. Broken rice, broken grains are already allowed. Rice is not allowed, but rice can be used. Sugarcane is being used, and they need a lot of water. So when you have to divert a lot of water into the cultivation of these crops, it also means that it might lessen the amount of water that we have for our own consumption. So that also brings in a scenario which is very difficult. So there are all these things, and that's why, especially with regard to food security, we need to understand the problem that biofuels can create. So that's why this is one aspect of the negatives of biofuel. Okay, so we had discussed this question in the last class itself, so I'm not going to discuss this again. Before going to the next part, that is nuclear energy, if you have any doubts from whatever we have discussed until now, please let me know, and then we shall move forward. Huh. So let me take your questions. What was this scheme, please? Uh, Scheme regarding we discussed two basic things. One, the biofuel policy, India's biofuel policy, and then we discussed the Pradhan Mantri Jeevan Yojana. Which one are you talking about? Here, this is a question for you. Explain lesser use of used cooking oil. So what I told you is that used cooking oil is very harmful for health. So when we are saying that there is a health benefit attached to the national biofuel policy, what we basically mean is that because used cooking oil can be sold by the restaurants to the various agencies that are there in a city, so then in that case, for a basic human health, it is better in that sense. Viability gap funding. So see, viability gap funding is when a government would want to provide extra financial support to certain to any kind of project to make it economically viable. So let me just write it also so that you don't forget it later. So when we say viability gap funding, this basically you can say it is a financial support mechanism provided by governments to make certain projects economically viable when they are not able to cover the cost costs through regular revenue streams. All right, so wherever this kind of a scenario comes in, that whatever funds were already given, they are not enough, or whatever budget was allocated, that was not enough, so then maybe by giving direct or indirect tax benefits, or maybe subsidizing something, so these kind of extra financial benefits will be provided so that the project can be made economically viable. So that is called as viability gap funding. Full form of MSW. MSW is Municipal Solid Waste. So Municipal Solid Waste Management. So the basically the domestic waste that we are generating, that is called as MSW. Improvement in air quality, because improvement of air quality, Nilanjana, basically is about uh, carbon dioxide emission reduction, or carbon monoxide emission reduction, sulfur dioxide emission reduction. So there are all these air pollutants that will be lesser because of this particular scenario. I mean, because of the use of biofuels. Biofuel generations explain. So biofuel generation, basically, when we are saying there are four generations, the first generation is where you are using food crops, anything that we can eat. If you are using the same for biofuel production, it is first generation. Second generation is non-edible. All right. So either non-edible crops or waste, municipal waste, agricultural waste, all this will be called as second generation. Third generation is largely algae based, where we are using algae for biofuel production. And fourth generation is experimental. There are various different experiments that we are conducting. Biofeedback are contributors to methane emission. Yes, Ravi, they are. Surplus means Then Prithvi, you have asked in viability gap funding, Government of India gives, but they have given the entire funding. Why are they giving again? So basically, many a times initially it is not even possible for us to gauge how much of money will be required, and if secondly, when we see the success of the project, we want to push it further, and in that sense also they want to give it extra financial support so that this project which is going well should continue on that path. So these are some of the reasons why. If we write answers and email it, will you evaluate it, sir? Yeah, of course. I've been trying to do that as much as possible, so I can. Carbon dioxide emission will be more by using the biogas? No, 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 no. It will at least reduce by 40%, if not more. Cost of making biogas plant is high, and also recently due to urbanization, bio waste like dung and plant waste is reducing. These can be a drawback of this energy. Not really, because it's not only about cow dung or plant waste, etc. We are generating so much of organic waste. We are generating so much of organic waste domestically, and all that can be used. And that's why it has been named as waste to wealth, because we can actually use this domestic waste and convert it into biogas. And even setting up of biogas plant, I wouldn't say that it takes a lot of effort and it takes a lot of money. It can be done at a very small scale as well, at an individual level, at an individual household level also it can be done. So but when cost is high, also I'll tell you, cost is high when we are setting up bio CNG plants, what the government of India is now calling as bio CNG. So now bio CNG is nothing different from biogas, more or less it's the same, just that the size, the scale of these plants are huge, and they cost a lot of money. But when it comes to individual biogas plants, it can be done very easily at a household level as well, at a very low cost. How reuse oil is harmful? See, when you reuse the oil, rather it is reheating of the oil. And let me just go to some details here. There is something called as the smoke point. All right, smoke point of any oil, whether you are using the mustard oil or the refined oils or ghee or whatever you are using for cooking. So there is something called as the smoke point. Now, how do we cook? When we are cooking something, we bring the temperature to the smoke point. Smoke point is when you start seeing smoke coming out of that oil. That should be the temperature at which you should cook. All right. Always. If you keep on heating it further, let's say you see that the smoke is already coming out, yet you already have kept your gas stove at high temperature, and a lot of smoke starts coming out. This is when chemically it starts to change, the oil starts to change chemically. And if the same oil has been reheated twice, thrice, multiple number of times, then it starts to lose its value. It starts to use lose some of its most important ingredients and nutrients, and this is when it starts to become harmful. Because any oil that you consume, if the oil has monosaturated acids or polysaturated acids or fats, they are good. If they have a lot of saturated fat, then it is bad. So now what happens is, when you have a lot of saturated trans fat, this is when anything for consumption is bad. So if let's say if you keep on heating it over and over again, the properties of the monosaturated fats and the polysaturated fats, they start to decrease, and that's why it is not fit for consumption anymore. This is what happens. This is also one of the basic reasons why you would prefer cooking something in mustard oil over a refined oil, or over something like ghee, because ghee would have more saturated fat, and refined oil would already have devoid a lot of nutrients from with the help of refining process, the extra refining that is done. And when you are using something like an extra virgin oil or cold pressed oil, which is also called as kachi ghani oil, so all these things, they are actually better for the kind of cooking that we do in our Indian ways. So thank you for coming to my TED Talks on Indian cooking. MNRE. MNRE is Ministry of New and Renewable Energy. How much blending target has been achieved till now? We already have achieved 20% blending targets in many of the districts, and one by one, it is being applicable in many others. In general, throughout India, we have achieved a total of, I mean, on an average, 12 to 15% of blending, and in some areas, 20% of the blending already has been achieved. So initially, our target was 2030. This also you should note that initially in 2018 the target was that by 2030 we'll achieve 20% blending targets, but then in 2021 the government made an amendment and brought down 2030 targets to 2025, and that's why they are in this process where they want that by 2025 end we should be in a position where 20% blending of bioethanol has been achieved all throughout the country. What genetically modified crops do for biofuels? We'll discuss this when we go to biofuels, sorry, when we go to biotechnology chapter in the next class. It will be better, you'll understand that better there. More carbon dioxide emission is dangerous always because it's a greenhouse gas. Will you cover the current dynamics of these topics through the lectures? Yeah, wherever necessary I'll keep covering all the current affairs as well. Methane production is harmful to the environment. How are we considering biogas as eco-friendly? Again, going back to what I told you when I discussed biogas, that when the combustion of biogas happens, combustion means in a manner adding oxygen. All right. So what we release is carbon dioxide. We do not release methane into the atmosphere. That is why I'm saying that it is better, because natural decomposition would have led to methane emission. But biogas, when the combustion of biogas happens, it leads to carbon dioxide emission. That's why it is better. How to generate biofuel individually and use it? Basically, creating a very small scale plant where you are cutting off oxygen supply. Cutting off only means that you have any kind of setup where passage of oxygen is not that easy. So then in that case biogas production automatically will start. Turns from unsaturated fat to saturated fat. Body can't break saturated fats and starts setting down precisely. So Neil, you have given what happens with saturated fats, why saturated fats are bad. Hmm. So let's move forward to our next topic, and this is nuclear energy. Now, in case of nuclear energy, the discussion that we are starting now, initially the discussion can be a little technical in nature. So I want your attention. I want your full attention for the first half an hour, 45 minutes. The second part perhaps will be easier to understand, but the first part of science of nuclear energy is a bit technical. So hang on. And if you have any doubts, keep asking. I mean, whenever we have a break, you can ask your questions then. So let's start with nuclear energy. Now, when we say nuclear energy, it means that this is energy which is coming from inside the nucleus, and that's why the name nuclear energy. Now, how are we saying that there is energy inside the nucleus? But before that, what do we mean by nucleus? Now, what you know, I'm sure, is that any atom has electrons, protons, and neutrons. I'm sure you know this. Electrons, protons, and neutrons. These are the three things that we have inside an atom. Now, in this atom also, the structure, if you see, there is a very small part inside an atom which is called as the nucleus. And this nucleus contains neutrons and protons, right? So protons and neutrons, they are inside the nucleus, and electrons, as you can see, electrons are orbiting this nucleus, being outside the nucleus inside the atom. So this is how the structure of an atom is, right? This is the structure of an atom, that you have protons and neutrons placed inside the nucleus, which is a very small space inside the atom. All right. And then you have electrons orbit around the nucleus, or let me say, they electrons revolve electrons revolve around the nucleus in various different orbits. All right. So this is what the basic structure. This is what the basic structure of an atom is, as you can see in the picture also. Understood? Understood this far? Now starts the complexity. That when we are saying that nuclear energy is the energy inside the nucleus, right? We are saying that this is nuclear energy. So nuclear energy basically is nuclear energy is the energy that the nucleus of an atom contains. All right. So nuclear energy is the energy that the nucleus of an atom contains. Now, in this scenario, let's try to understand how exactly is there energy inside this nucleus. Now, when we look at the understanding of the nucleus, if you go back into the history of understanding of the atom, initial theories, if you see theories 500 years back or 700 years back, you'll see that the atomic theories say that there is nothing inside an atom. Atom is the smallest indestructible part of an of matter. If you remember something called as Dalton's atomic theory, you might have studied once upon a time in your class 8th, ninth, etc. So Dalton's atomic theory says that atom is the smallest indestructible part of an atom, meaning that there is nothing inside atom. Inside atom is the smallest. But then we saw that there are various discoveries that happened, and these different discoveries, they started explaining the atom better. So first there was discovery of electrons. There was discovery of electrons, which was done by J.J. Thomson. Electrons were discovered by J.J. Thomson. Now, what J.J. Thomson basically did is that he gave a theory, and this theory that was given by J.J. Thomson was that an atom is, you can say, it was called as a plum pudding model. Let's say like a watermelon. If you see a watermelon, if you cut the watermelon, what do you see? That there is a reddish part, correct? There is a reddish sphere which has a lot of embedded seeds in it, correct? A lot of embedded seeds. So what he proposed is that, look, atom is not indestructible. There are particles inside the atom, and these seeds are like negatively charged particles. These are negatively charged particles or electrons. He did not define protons, he did not define neutrons, he just defined electrons. And according to him, the entire red portion that you have in this watermelon, the entire red portion itself is positively charged, and only these seeds are negatively charged. This is what he said, right? This is what he proposed. So in a manner you can say that this led to the discovery of electrons. But then we see that discovery of protons also happened, and discovery of protons is done by Ernst Rutherford. Discovery of proton is done by Ernst Rutherford, where Rutherford properly defined the nucleus. He defined that, look, inside the atom, there is a very small portion. And inside this very small portion, a very small space, you have all the positive charges. So all the positive charges are there inside this small space, and majority of the atom outside this small space is empty. This is where electrons are present in their various orbits, but this is largely empty. Largely empty, only there are certain orbits and there are certain electrons in that. But at the center, there is a very dense space which has all the positive charges at once. And these positive charges are protons. And he was the one who named them as protons. Although there is very interesting, there was another experiment that was done almost 20 years before Rutherford, and this was done by Goldstein. And Goldstein also had defined positively charged particles, but in a very different context. There was an electric discharge tube experiment that was done by him, and that experiment is where he proved that there are certain positive charges also, but not as a part of an atom, not in a manner that Rutherford did. So that's why largely when we talk about who discovered protons, we take Rutherford's name and not Goldstein's name. But even Goldstein had proved the existence of positive charges. Now, so protons were discovered, electrons were discovered, and we felt happy about it that now we have positive charges, we have negative charges, so we know how things are balanced. But then, when we look at the mass, this is where we understand that there is something else. And then discovery of neutrons happened. This was done by James Chadwick. This was done by James Chadwick, the discovery of neutrons. Now, where does discovery of neutron come from? We have already seen that, okay, fine, these are positive charges, negative charges, but then comes the concept of an isotope. Can you tell me what do we mean by isotope? Anyone who remembers? What do we mean by an isotope? Same atomic number and different atomic mass. Correct. So isotope, atoms of the same element with same atomic number and different mass number. Now, one more question for you. Can you tell me what is atomic number and what is mass number? What do we mean by atomic number and what do we mean by mass number? Atomic number is number, yes, atomic number is number of protons. This is number of protons. And what is mass number? What is mass number? Yes, number of protons plus number of neutrons. So number of protons plus neutrons is called as mass number. Number of protons is called as atomic number. Can we say that atomic number can be defined as number of electrons as well? Can we say that atomic number can be defined as number of electrons as well? Yes or no? So many of you have given the correct answer. That is no. Can you tell me why not always? Why can't we? Yes, Shahid, you have given the correct answer. Tirtha, you've given the correct answer. Satyapal, you've given the correct answer. Chanchal, you have given the correct answer. Wonderful. So what we basically see is, look, in a neutral atom, where there is no charge, there is no extra charge, number of protons and number of electrons are the same. So there you can say that, okay, fine, number of electrons also can represent atomic number. But number of protons, remember this, number of protons is the most important property of any element. If the number of protons change, the element itself changes. If the number of electrons change, it need not change the element. But if you go on from one proton to two protons, it simply means that you have moved on from hydrogen to helium. When you have six protons, you have carbon. When you have eight protons, you have oxygen. So number of protons is what defines an element. So that's why number of protons is the most important property of any given element, and that's why atomic number becomes the identifier of any element. So now what we mean by an isotope is atoms, that's why, of the same element, because they have the same atomic number but different mass number. And this is what we observed, where we thought that, okay, there should be something else. That when we look at the three different forms of hydrogen, or what we can call as isotopes of hydrogen, we have hydrogen, deuterium, and tritium, where we can represent them like this. This can be called as 1H1, this can be called as 1H2, and this can be called as 1H3, where 1H1 represents, this has one proton and zero neutrons. This has one proton and one neutron. And this has one proton and two neutrons. So what you see here, this is the mass number. This is mass number. And what you see here, this is the atomic number. So atomic number is 1 for hydrogen. That's why number of protons in all the three cases is the same. That is 1. But number of neutrons can change. That's why mass number can change. And then these are called as isotopes. So now, from our understanding of the isotopes, we discovered that, okay, there is something else inside the nucleus which doesn't carry any charge. Because if neutrons had a charge, then it would mean that they would also add the charge. They would either become positively or negatively charged. But that's not happening. It is only adding mass, right? It's only adding mass. So it means that there must be something inside the nucleus which is adding mass to this nucleus, but it is not adding any charge. That's why the name neutron, from neutral, because it is neutral. It is neither positively charged nor negatively charged. It is neutral in its charge. It doesn't carry any charge, and hence the name neutron. So then the discovery of neutron happened, and then you can say, in a manner, this summed up the atomic structure. This summed up the atomic structure. So now we knew that, okay, fine, there are all these things that we have in any given atom. Now this is where we go to one more step, and our understanding of something called as the nuclear binding energy and the concept of mass defect. Now what changes? Until now, we knew that, okay, fine, we have the atom, and we have inside the atom we have the electrons which are orbiting in their own orbits. They have various different shells in which they are placed, and then you have the nucleus, and inside the nucleus we have protons and neutrons. Now what was seen here was something very extraordinary. Let's say we have any nucleus, all right? We have a nucleus which has one proton and one neutron, all right? Suppose that this one neutron is of 10 grams. This one neutron also weighs 10 grams. And you have this nucleus which has only one proton and one neutron. So then that nucleus should be 20 grams, right? This nucleus should be 20 grams. But what we are seeing is that it's not actually 20 grams, but rather, let's say, 15 grams. These are all examples, these are not actual figures. Just 15 grams. Now this was very perplexing, that why is it happening? I mean, let's say if it was 25 grams, we could have said that, okay, fine, there is something extra, and we haven't been able to account for that extra thing, and that's why 25 grams. But when we know there is one proton, there is one neutron, and they were 10 grams each, then why is the mass not 20 grams but 15 grams? So the scientists did not understand what was happening here, and hence they named it as mass defect. Okay, fine. There is some kind of defect in the masses of these subatomic particles, which is leading to a problem like this. So that's why they called it as mass defect. Now, when it comes to, so that's why if you look at the actual figures, so mass defect, that's why it's a difference between the actual mass of an atom and the sum of the masses of protons, neutrons, and electrons. So if you see as an example, mass of helium atom is 4.00260 AMU, or atomic mass unit, but the mass of its constituents in total becomes 4.03298. So that's why all the electrons, protons, and neutrons together, they make up this much, but the atom as a whole, this is something different. So that's why the missing mass is equal to, this missing mass is equal to the binding energy holding the atom together. So this is where the concept of nuclear binding energy comes. That what we understand is that this mass, the 5 gram mass that is being, which is missing here, this actually is mass that has gotten converted to energy. All right, this is the energy that the nucleus is using to ensure that all the protons and neutrons can be kept together inside the nucleus. To keep nuclear parts together, this binding, what is binding? To bind, right? To ensure that it doesn't go out. So that's why it is called as binding energy or nuclear binding energy. So that's why nuclear binding energy, energy with which the nucleus binds together all the subatomic particles like protons and neutrons. So all these particles, they are bound together with the help of this nuclear binding energy. So that is the role of this nuclear binding energy. And this 5 grams that we thought were being lost, they were not actually being lost, but rather they are the ones which are being used to hold this atom together. Now, how do we come to know about this? With the help of a very famous scientist, a very famous scientist whose name will keep taking probably in every chapter, Albert Einstein. And Albert Einstein explained this. When the scientists thought that now they know everything, Albert Einstein said, wait a minute, I have something for you. And this something was this very famous equation. Have you heard of this equation? E is equal to mc squared. I'm not asking whether you know what the meaning is or not. Probably you do not know what the meaning is, but you might have heard of it, right? You might have heard of it, that yes, there is a very famous equation that goes by E is equal to mc squared. Now, this is basically something that Einstein had explained, that until now it was mass defect. Until now it was mass defect, but then Einstein came forward and said, no, this is not mass defect. But this is what happens, that energy and mass, they are interconvertible, and mass should be seen as a form of energy. We should look at mass as a form of energy, and this is how they are interconvertible. This E represents energy, this M represents mass, and this C is speed of light. How much is speed of light? 3 into 10 to the power of 8 meters per second. So this is what he explained. Now we were able to account for it. That when we are looking at how much energy is being released or absorbed by this nucleus, how much rather released by this nucleus is equal to the lost. I mean, when we put that in this equation, we see that it is equivalent of that mass. So now he explained it. Now he explained it that okay, now this is what it is, with the help of the theory of special relativity that was given by Albert Einstein. So this now made things clear. This now was able to make things clear for a lot of different scientists, because a lot of them, they did not understand what was happening here, and all these things now started making sense in their heads. So this is what happened. Now, before we proceed, any questions if you have from here? I'll take your questions. We'll take a break, and on the other side of the break, we'll start with that next topic, that is radioactivity. If you have any questions, please let me know. I am not understanding this theory. So this theory basically is nothing but we are giving a simple equation of how mass and energy are interconvertible. That if you, for example, if you have 1 kg mass, all right, let's say we have mass of 1 kg. We know that the value of speed of light is 3 into 10 to the power 8. So it means that energy will be equal to 1 into 3 into 10 to the power of 8 squared, equal, that is 9 into 10 to the power of 16 joules of energy. This is basically what he explained. Did Einstein discover subatomic particles? No. We discussed about who discovered the subatomic particles. He did not. What is mass defect? I'm repeating it again. Mass defect basically is the difference between the actual mass of the atom and the sum of the masses of all the protons, neutrons, and electrons that you have inside the atom. Please explain binding energy. Binding energy is the energy with which the nucleus binds all the subatomic particles together, all the protons, neutrons together, so that they do not escape out of the nucleus. So for that, to ensure that the kind of energy that is exerted by the nucleus is called as the nuclear binding energy. What's this equation used for? This equation simply tells you about the relation between mass and energy. That's it. Number of neutrons are varying. See, it depends on a lot of internal factors and the kind of forces that are there inside the nucleus. So because of that, many a times we see that the nucleus becomes unstable, and because of that instability, the neutrons might move in or out. Where 5 gram gone? That's why I told you that those 5 grams, they converted into energy. Um, Arti, for any issue that you are facing, please write to me If they are not getting resolved, I'll forward it to the required team. And even then, if it is not, please let me know. rashesh.kumar@byju's.com. Binding energy, once again, I'm repeating, binding energy is the energy that is required by the nucleus to bind all the particles together to ensure that nothing goes out. So, for that, the kind of energy that they are exerting, that's called the nuclear binding energy. This happens always that these 5 grams get converted into energy. Yeah, that will always be the case. Then Harshita, you asked, it means that the energy which gets released from the nucleus was the mass defect earlier scientists defined. Yes, exactly correct. Class is on interesting. Please don't break. See, if I continue for long, there are others also who probably do not come from the same background, and it might become difficult for them if I keep continuing. So that's why. And also, I also need some rest. Hmm. When will the two cancelled classes be compensated? I'll keep continuing until the time my classes are finished. I'll keep continuing. How 9 came from in the equation? 9, because 3 squared is 9. That's why. Annotated PPTs. I'll check with the team about annotated PPTs if there's any issue. Hmm. Protons and electrons are the same. No, 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 they are not same. First, their charges are opposite. Protons are positively charged, electrons are negatively charged. Secondly, protons are heavier as compared to electrons. Protons are almost 2000 times heavier as compared to electrons. So they are not same by any stretch of imagination. Will you take all the mains question discussion also? Yeah. At the end of the class, I'll do that. Don't worry. I mean, if you see this PPT itself, the last portion of the PPT, the last few PPTs, if I'll show you, I have the previous year questions that have come in this particular chapter, but we'll go there when required. Don't worry. I'm an offline student, recently converted into online. This class is genuinely amazing. Oh, thank you. I would have come for your offline class also, I think, in that case, but I had some issues going on in my home because of which I've not been able to take certain classes. We will further study theory of relativity and equation detail. No, no, no. That's way beyond what we need for our examination, so we'll not go there. Hmm. So let's take a break here. It's 6:29. Let's be back by 6:40. Let's be back by 6:40 and then continue from there on. Welcome back, everyone. So now we know the basics. We know that okay, there is something called as nuclear energy, and we know the source of that nuclear energy. That where does this energy come from? Now, when it comes to nuclear energy, it shows itself in three different ways. One called as radioactivity, another called as nuclear fission, and the third one is nuclear fusion. So we'll try to understand what is nuclear fission, what is nuclear fusion, and what is radioactivity. Because these are the three ways in which we see the release of nuclear energy. All right. These are the three ways in which nuclear energy is released. Now, understand this when it comes to radioactivity. Now, radioactivity, how do we define radioactivity? We say that any unstable nucleus undergoes a decay. This is referred to as radioactive decay. The key word here is unstable nucleus. When do we say that a nucleus is unstable? All right, how do we say that a nucleus is unstable? So there are three ways in which a nucleus can be unstable. How? One, if first is when number of protons in the nucleus is very high. When the number of protons in the nucleus is very high, then we say that it is unstable. Another way when we say that it is unstable is when number of protons is not equal to number of neutrons. All right. When the number of protons is not equal to number of neutrons, it is called as unstable. And then there can be the third case when nucleus has more energy than usual. When nucleus has more energy than usual, then also it is said to be unstable. All right. So these are the three cases in which one can say that a nucleus is unstable. So when you have the first case, when the number of protons in the nucleus is very high, this is when it is called as alpha decay. This is called also called as this. We can also write like this, alpha decay. So this is the first kind of radioactivity called as alpha decay. Second kind of radioactivity is when the number of protons is not equal to number of neutrons, and this is called as beta decay. This is called as beta decay. And then when it comes to the third case, that is nucleus has more energy than usual, this is called as gamma decay. This is called as, let me use another color probably. This is called as gamma decay. So these are the three cases. These are the three different types of radioactivity. So radioactivity will be seen in any nucleus when the nucleus is unstable. How do we say that something is unstable? On these three criteria. Either the number of protons is very high, or the number of neutrons and protons are not the same, or the nucleus has more energy than usual. These are the three cases in which we'll say that any given nucleus is unstable, and if it is unstable, it can undergo decay, which is called as radioactive decay. So now just understand one by one what exactly happens in these cases. Alpha decay, what did I say? Alpha decay would happen when the number of protons is very high, right? When the number of protons is very high. So this is something that we will see in heavy nuclei. This is a property of heavy nuclei. Now understand what's happening here. All right. The number of protons that we have in a given nucleus does not increase in the same ratio as the size of the nucleus. Just let me give you an example. Suppose that this is a class right now. Let's say it was an offline class. All right. If it was an offline class, and suppose that I am sitting and giving this lecture in a class which has a seating capacity of 100, and suppose that you all are 100 in this class, so there are 100 students, the or let's say the seating capacity is 150, and there are 100 students in the class, so you can all sit very easily, right? You can all sit very easily because there are 150 seats and there are 100 students, no problem. But then suppose that for some reason I'm not able to take the morning batch, and I ask the students of the morning batch also to come and sit in the evening batch itself. There are 100 students in the morning batch also. Now what happens? There are the seating capacity is 150 and you have 200 students. So can I make everyone sit? Probably not. What happens next? You will say that, look, we are the original owners of this class. The class was being conducted for us. So you people coming from the morning batch have no business here. So please get out. And maybe you start fighting and you throw them out. So this throwing out also happens in the nucleus, because nucleus has a certain capacity, and when the number of protons keeps on increasing with every new element, the size of the nucleus does not increase in the same ratio. So the numbers are increasing, but the size is not increasing. Now what happens? There will be a time that when for the nucleus it's not possible to take in any extra proton, and at the same time, also remember that all the protons are positively charged, correct? And I'm very sure that you all have read this somewhere in your childhood, that like charges repel each other, unlike charges attract each other, correct? Meaning that if you have a positive and a negative charge, they would attract each other. And if you have two positive charges or two negative charges, they would repel each other, right? So this is basically what we see here, that nucleus size is small, number of protons has increased a lot, so there is a lot of repulsion inside this nucleus, and the size even does not uh, has the size is not enough to fit all the protons together. So what happens? Now some of the particles will start getting out, they'll start going out of this nucleus. This is precisely what happens in alpha decay, where you have a heavy nucleus where the number of protons is very high, and that's why it is not that is when this nucleus becomes unstable. And especially we see this above atomic number 83. Especially this is something that we see at above atomic number 83. So that's why alpha decay, the mass number of the product nucleus is 4 less than that of the decaying nucleus, while the atomic number is decreased by 2. This is what happens. If you see this 240 has become 236, that is minus 4, and this 94 has become 92, that is minus 2. So what has happened? That mass number has decreased by 4, atomic number has decreased by 2. So how many protons and how many neutrons have been released? Can you tell me this? How many protons and how many neutrons have been released? Kartik Raj, you've given the correct answer. Tirtha, you have given the correct answer. Shahid, correct answer. How many protons and how many neutrons? Shweta, correct. Shimna, correct. Chanchal, correct. Many of you have given wrong answers. I'm not taking the names. But remember, we said that this is what? This is atomic number and this is mass number, correct? What did we say? Mass number is what? Atomic number is number of protons. Mass number is what? Mass number is number of protons plus neutrons. So number of protons is 2. 2, right? Minus 2 is happening, so 2 protons. So how many neutrons? 2 more, because mass number is protons plus neutrons. So minus 4 is 2 plus 2, correct? Minus 2 is what? 2 plus 2. So that's why 2 protons and 2 neutrons have been released. So this is what is happening, and that's why alpha particle is said to be equivalent of helium nucleus. This is what helium nucleus is: 2 protons and 2 neutrons. 2 protons and 2 neutrons, just after hydrogen. Hydrogen having 1 proton. Helium has 2 protons. So 2 protons and 2 neutrons is helium. So this is what is happening here in alpha decay. That 2 protons and 2 neutrons have come out of the nucleus. Right? 2 protons and 2 neutrons have come out of the nucleus. So this is exactly what is happening here. And this is what alpha decay is. Then we have beta decay. Now what did we discuss about beta decay? This happens when protons, the number of protons is not equal to number of neutrons, and it can happen in heavy nucleus or light nucleus. Doesn't matter. Just that in whatever nucleus the number of protons is not equal to the number of neutrons, this will happen. Right? This will happen. So in beta decay, nucleus spontaneously emits an electron or an positron, and mass number remains unchanged. Now this is very, very important. Mass number remains unchanged. So for example, if you see carbon 14 to nitrogen 14. Now when we have carbon 14, carbon 14 has 6 protons and 8 neutrons, which makes it 14. Now obviously the proton and the neutron number is not the same. So for attaining stability, you need the same number of protons and neutrons. So which is 7 and 7, because mass number remains unchanged. So this is 14, which is, this basically is nitrogen 14. This is nitrogen 14. And in the same case, if you look at the other case, carbon 10 to boron 10. So carbon 10 means what? Quickly, can you tell me how many protons and how many neutrons? How many protons and how many neutrons in carbon 10? Number of protons will still remain the same. Yes, neutrons is 4, correct. So protons 6, neutrons 4, which is 10. And now to make it equal, what do we need? 5 protons and 5 neutrons, which is 10, meaning converted to boron 10. So this is what the conversion is like. So in case of beta decay, we just want to attain stability by having equal number of protons and neutrons. Now the question is, when we see this, that okay, this 6 has become 7 and this 8 also has become 7, plus 1 and minus 1. Similarly here, minus 1 and plus 1. Does it mean that a proton or a neutron is coming from somewhere outside? Outside the nucleus, something is coming. So when you have 6 protons to 7 protons and 8 neutrons to 7 neutrons, does it mean that one neutron has gone out of the nucleus and one proton has come from somewhere outside the nucleus? The answer is no. What happens very weirdly inside this nucleus is that one neutron converts into a proton. So in the first case, a neutron converts into a proton. Neutron converts to proton. And don't ask me how. Way beyond our expectations in this class. Even this you need not know. I'm just giving you this piece of information, not required for your examination. And why am I giving you this information? I told you already that number of protons is the most important property. So you cannot just bring a proton from outside or send a proton outside so easily. It is a very, very difficult process. So only happens in a very specific circumstance. It cannot really happen very easily. So that's why we see this kind of a scenario where either a proton converts to a neutron or a neutron converts to a proton. So this is how internally their uh, structure would change and they would become stable. So this is beta decay. And then after that we have gamma decay. So gamma decay is when a nucleus in an excited state spontaneously decays into a ground state. This is basically called as gamma decay. Now when we say excited state means more energy than usual. Excited state means more energy than usual. So this is basically what we call as excited state. So in case of gamma decay, this is what happens, that you have a nucleus in excited state which comes back to the relaxed state by losing some energy. All right, by losing some energy. So excited state is unstable. You might have seen small children who keep jumping around. So when they are jumping around, they are unstable. And sometimes to bring them back to stable energy level or their relaxed state, there is something that many of the parents would do, and then they would come back to their relaxed state. So that coming back to the relaxed state is what we call as gamma radiation, so gamma decay. So there are ways in which parents do it. I neither approve or disapprove of those methods. So excited to relaxed nucleus, when this transition happens, this is called as gamma decay. Now, overall, when it comes to alpha, beta, or gamma decay, these are three ways in which naturally we see that transition happens, or naturally energy is emitted. Naturally, because naturally it is unstable, so naturally we see that the energy is emitted out of the nucleus. So these are the natural ways. And then there are ways which we can instigate, the ways in which we can generate energy from the nucleus. And that is where we have nuclear fission and nuclear fusion. So let's try to understand what do we mean by nuclear fission and nuclear fusion. Now, first, when it comes to nuclear fission, but before this, okay, any question from radioactivity? Anything that you want to ask from whatever discussion we had in the last 20 odd minutes? I didn't get alpha decay. Then you have asked. So see, alpha decay basically is when we are saying that the nucleus has become very heavy. Nucleus is not able to accommodate more. It has more protons than usual. It has more particles than it can accommodate. So what happens is that some of the particles will come out of the nucleus. That is called as alpha decay. And this precisely happens when we go beyond a certain limit, especially when we go beyond atomic number 83, which is bismuth. When we go beyond that, then it starts becoming very unstable and might throw out some of the particles to become stable. That is alpha decay. Then Vishant, you have asked, positron is the particle which has same mass as electron but has opposite charge. Yes, precisely correct. And is a very unstable particle. Like electron is stable. All right, electron is not unstable. Positron is a very unstable particle. These reactions can be asked in the exam. No, these reactions will not be asked in the exam. Just remember the theory around it. These equations I've just given just for a better clarity and visualization, but they wouldn't be asked in the exam. If they have to ask something in the exam, they would ask you the theory around it, all the stories that I've been telling you. Explain once again radioactivity and alpha decay. Alpha decay, I just told you, radioactivity is, just remember this, that whenever you have any nucleus that has become unstable, the ways in which it can become stable is radioactivity. It would release certain energy to try and become stable. That is called as radioactive. Is it important topic for exam? If it was not important for the exam, I wouldn't teach you. Questions have come from all these topics that we have discussed, and not only in UPSC, even in your state PCS examinations, questions have very often come from these topics. Could you explain gamma decay slightly further about what energy is lost? See, energy basically is in terms of electromagnetic radiations. All right, these are electromagnetic radiations that will be lost. So that extra energy also comes from some kind of, you can say, kinetic energy many a times, some kind of energy that is in terms of photons or electromagnetic energy particles. So those energy particles will be released outside. When any atom is unstable, will it always try to go to the stability or remain what it is? Yes. So, to answer your question, Aditya, we are, I mean, just one thing to change. We are not talking about an atom, but rather we are talking about a nucleus. All right. Every discussion that we are doing henceforth, we are doing about the nucleus and not the atom itself. Now, here, uh, will it always try to be stable? The answer is yes. Just like everybody in our lives, we all want to be stable in our lives. Similarly, any atom or any nucleus also would always try to be stable. So, if it is unstable, by rule, it will try to become stable. How we will come to know that when we have to reduce proton or add, we do not do anything. We do not, this is natural. All right, it will happen on its own. The the nucleus itself will try to undergo alpha decay or beta decay or gamma decay. We have no role in it. They will do it on their own. Why do we consider number 83 only? We do not consider, we have observed this. We have seen that above the atomic number 83, the instability is a lot more. And that's why the chances of alpha decay is a lot more. What type of questions we expect from this topic for prelims? The basic definitions. The basic definitions, the basic examples that we have seen, only that much. Nuclear fission and fusion are part of radioactivity? No. The answer is no, they are different. Hmm. So let's move on. The next topic is nuclear fission. Now, can you tell me this first? Do you know what the meaning of this term fission is? What do I mean by fission? The dictionary meaning of fission? Breaking something, separating, split. Correct. Correct. So, fission means to break, right? Fission means to break or split, right? This is the basic meaning of fission, English meaning of fission. So when we say nuclear fission, means what? Nucleus is breaking. What did we see in radioactivity? That some particles were releasing, right? Couple of protons, couple of neutrons, some energy particles, right? Only some particles were being emitted. But here we are saying that the nucleus is breaking. So when the nucleus breaks into two or three parts, while releasing enormous amount of energy. This is called as nuclear fission. All right. So process whereby an atomic nucleus breaks up into two or more major fragments with the emission of two or three neutrons. This is called as nuclear fission. Got it? So this is basically how we see, and it is accompanied by the release of energy in the forms of gamma radiation and kinetic energy of the emitted particles. How that happens, we'll discuss that. So when it comes to nuclear fission, something like this happens. All right, we have a nucleus of uranium 235. Uranium 235 meaning that uranium with atomic mass or mass number being 235. We bombard it with a neutron. So what happens is we have this uranium, all right, this is uranium 235 nucleus. We take a neutron and we bombard it towards it. Now, as it is bombarded towards this uranium 235, it goes and sticks to nucleus of uranium 235. As it sticks to uranium 235, it becomes uranium 236, one extra neutron. This is what the mass number is, number of protons plus neutrons. Number of protons does not change, one extra neutron has been bombarded. So uranium 235 becomes uranium 236. Now this uranium 236 is highly unstable. It is very, very unstable. It is so unstable that it now breaks. It breaks into two fragments. What are these two fragments? These are krypton and barium. So it has now broken into two parts, that is barium and krypton, while releasing a lot of energy. This energy is in form of gamma and kinetic energy. So these two combined, they are releasing this, basically this process has released a lot of energy. Apart from releasing so much of energy, there are three extra neutrons that have been released. How exactly? If you do the simple mathematical calculation, you will see this. You have 236 on this side, right? On the other side, you have how much? 92 plus 141, which is equal to 233, correct? So there are three extra neutrons. Apart from these two elements, there are three extra neutrons. Now, what happens here on is something very interesting. These three extra neutrons, they set up a chain reaction. They would set up a chain reaction. Why? Because they would just go on, keep on bombarding. You do not have, just remember this, you do not have one single nucleus here. Even if you have 1 gram of uranium, even if you have 1 gram of uranium, do you know how many particles 1 gram of uranium can have? If you remember, again, I'm just going back to your school days. If you remember the mole concept, if you remember the mole concept, there was something called as Avogadro number. You might have studied about Avogadro number back in your class 9th and 10th. 6.022 into 10 to the power of 23 particles. Correct? In 1 gram atomic mass of carbon 12, 6.022 into 10 to the power of 23 particles. Correct? So now this basically is what? These are the number of particles that you'll have in just 1 gram. And if you calculate the number of particles in 1 gram of uranium, it comes out to be somewhere around 10 to the power of 21 such particles. So 10 to the power of 21 particles are available. So just imagine how much of reaction can happen. Now a chain reaction has been set up. What happens next? What happens next? Each and every one of these three neutrons will go and bombard three more of uranium 235. From there on, you get three more at each step, right? You get three more at each step. So 3 became 9, 9 becomes 27, 21 becomes 81, 81 becomes 243, 243 becomes 729, and so on. Correct? And so what happens? And every step, what is happening? If one unit of energy was produced here, 3 units of energy are being produced, then 9 units of energy, 27 units of energy, 81 energy units, and so on. So within seconds, enormous amount of energy is being produced from here. Huge amount of energy within seconds is what we are getting out of this process. Now, it becomes very crucial for us to understand something, that we have set up a chain reaction. If we control this chain reaction, we get the amount of energy that we want for maybe electricity generation. If we do not control this chain reaction, if this chain reaction goes uncontrolled, you create an atom bomb. This is where you create an atom bomb. So, creating an atom bomb versus using this nuclear energy for electricity generation, the only difference is whether you are controlling the chain reaction or not. If you are controlling the chain reaction, you get electricity. If you don't control the chain reaction, you set up an atom bomb. This is precisely what a bomb will be when you don't control the chain reaction. You'll just let it go. And that is what we have seen in case of the atom bomb that was dropped on Japan by the US. There were two atom bombs that were dropped, and the kind of devastation that it caused in the two cities of Japan is unimaginable. And that is all about whether you have controlled the chain reaction or you did not control the chain reaction. This is where concept of critical mass comes in. Critical mass. So critical mass is the mass of the given reaction. Critical mass is the mass of the given uranium 235 sample at which you can carry out a controlled chain reaction. If you have more than this, then you cannot control the chain reaction. If you have less than this, even then you cannot control the chain reaction. If you have less than critical mass, so critical mass, just remember, critical mass for a sustained chain reaction. So critical mass is the smallest amount of fissile material needed for each fission reaction to produce at least one more fission reaction on an average. So what, if I have to write in a simplified form, I would say that critical mass is the mass of uranium 235 required for a controlled chain reaction. All right. So critical mass is the mass of uranium 235 that is required for a controlled chain reaction. If we go above critical mass, the reaction goes uncontrolled. You are moving towards making an atom bomb. And if it is below the critical mass, then the reaction would stop very quickly. It will stop within a couple of minutes. So then you cannot sustain the chain reaction. So that's why to have a sustained controlled chain reaction, we need to be at critical mass. And that's why once in a while you will see news like this. This is a news from December 2023. Kakrapar nuclear plant achieves criticality. So criticality means that now we have understood what is the critical mass of this reactor. How much of uranium 235 we need to carry out reactions in a controlled manner in this reactor. And only when criticality is reached in any given nuclear plant, that is when uh, you start the operations of the nuclear plant. Otherwise we do not start the reactions, or we do not start the operations of the reactor. So it means that, meaning critical mass in the reactor has been achieved. Right, this is what it means. So this is what we mean by criticality. So criticality was achieved, and this has happened in the Kakrapar 4. This is the Kakrapar 4 reactor. This is in Gujarat near Surat. So this is where we see that this is something that we do. So that's why first thing, very, very important safety measure is to attain criticality. All right, is to attain criticality. And once we have attained criticality, then there is another process which is very, very crucial, and this is enrichment. Now let me tell you what is enrichment. What is the meaning of enrichment? Now uranium, we are using uranium, correct? Uranium is naturally available inside the Earth's crust. We can mine for uranium. Mining is done, and with the mining of uranium, we get uranium ore. Now, this natural uranium that we get, the natural uranium that we get from uranium mines, it is a mixture of two types of uranium, two isotopes of uranium rather, uranium 235 and uranium 238. All right, uranium 235 and uranium 238. So natural uranium is a mixture of uranium 235 and uranium 238, where we know that uranium 235 is what we are using in the nuclear reactions. Nuclear I mean uranium 238 is not usable. Uranium 238 cannot be used for nuclear fission. If you bombard it with an extra neutron, the extra neutron will just go and be absorbed by uranium 238. Nothing will happen. All right, nothing else will happen. So it will not split. Naturally, radioactivity will keep on happening, but it will not split. It will not break. All right. So that's why uranium 238 is not useful. I mean, for nuclear fission, it is not useful. Uranium 235 is useful. Now, the problem here is that out of this, what we have, only 0.7% is uranium 235 and 99.3% is uranium 238. So, if let's say the things were reversed, then it would have been a wonderful scenario for us. That if we had 99.3% of uranium 235 and only 0.7% of uranium 238, that would have been a great thing for us. So what it means is that out of every 100 grams of uranium that we are mining, only 0.7 gram out of those 100 grams is actually useful for us. Rest is not. Rest of the uranium is not. So that is where the problem lies. And to solve for this problem, we use the process of enrichment. We use the process of enrichment. So what is enrichment? Enrichment is the process of increasing the proportion of uranium 235 in the mixture of uranium 235, uranium 238. Right, so increasing the proportion of uranium 235. So what happens is that from 0.7%, we increase it to 3 to 5%. We increase it to 3 to 5%. Can we not do more? Why 3 to 5% only? Why not? If conversion is possible, convert 100%. Convert 100% of uranium 238 to uranium 235. Why not do that? We don't do that because going beyond 3 to 5% means that you are not going to use it for electricity generation, but rather you are going to make an atom bomb out of it. Because now beyond 5%, the uranium 235 nucleus starts to become unstable, starts to become very unstable. And once it starts to become unstable, this is where you start to create weapon grade uranium 235. You are basically, if you are any country or any organization, if they are doing the enrichment beyond 5%, it means that they are creating an atom bomb, and they are not actually going to use it for electricity generation. This is precisely what happens. So uranium with an abundant amount of uranium 235 is called as enriched uranium. Now, in this context, you might have seen in the last couple of years, we have seen this kind of news, especially in the context of Iran. IAEA chief raises alarm over Iran's 60% uranium enrichment level. This was in the news just a week back. And just today, officials from IAEA, they have reached Iran. They have gone to Iran to check. Just today this has happened. Tomorrow perhaps it will be in the newspapers. So IAEA chief, he actually has gone to Iran, and they have raised concerns with regard to Iran's 60% uranium enrichment level. And very soon they might reach 85 to 90% enrichment, which basically is weapon grade uranium. So that would mean that now Iran has a nuclear weapon. In very simple terms, this is where Iran is right now, that Iran is now very near having a nuclear weapon, an atom bomb. And that's why today we see that the entire dynamics around Iran also has been changing. Recently, you might have seen this, that Israel, we know that there is the issue between Israel and Hamas going on right now. And in that, uh, we know that Iran has been using a lot of its proxies, a lot of the militia, a lot of the militia groups that we have, like Hezbollah, etc. They are all very well paid by Iran, correct? And in this particular scenario, we have seen that there have been a lot of shadow attacks that Iran has been doing against Israel for a very long time. Now, what happened last month is that Israel launched an attack in Damascus where some Iranian officials were killed. So this is, you can say, for the first time where a direct attack on an Iranian has been done. Although it was done in Damascus, it was not done inside Iran. But then a lot of defense experts, geopolitical experts all across the world, they were saying that Iran will do nothing. Iran will not do anything because Iran is not as strong as Israel is. Iran does not have the kind of defense that Israel has. So Iran will do nothing. But what did we see? Just a week later, we see that Iran attacks Israel, launches more than 300 drones and missiles towards Israel. Iran does it. Iran, for the first time, launches a direct attack against Israel. At least for the last 50 odd years, nothing of this sort has been done. Why? Because Iran also realizes that slowly and steadily they are also rising in power. It's not that they are as weak as they used to be. Very soon they would probably declare, or maybe not declare, but the world will know that they have weapon grade uranium. They know now how to create an atom bomb, and they become a nuclear power. And this is when they start becoming stronger in this area, in this region. So they start to become a regional power, a regional superpower, if I may say so, in in the context of West Asia. So that is why we have seen that Iran now is gaining that confidence that we can do this, we will do this, because we are, first and foremost, they are also being backed by certain countries like Russia and China. They have the backing of Russia and China. At the same time, they have seen that how uh, weak in certain scenarios US and the Europe have been, and that's where they are now getting that confidence to go further. So overall, that's why we see that these kind of dynamics are actually uh, developing in the West Asian region, or what we call as the Middle East. So we have to see what happens and where we go from there on. uh, and also there is the other part also, that we all know that Israel has Iron Dome. So Iran also knows that even if we are launching an attack on Israel, the drones and the missiles, they are going to be countered, and it's not actually going to cause any, uh, you can say, casualty on Israel. So that also is something that Iran knows. So that's why that also is a thought process that Iran knows that even if they are launching an attack, it's not going to cause any harm because of the Iron Dome system, the defense system that Israel has. And that is precisely what happened. And every time that happens, Israel pays a lot economically, because the Iron Dome mechanism, the Iron Dome system that they have, that actually is very costly system. It's a very costly system. So it's a huge economic dent on Israel every time Israel has to use the Iron Dome. And that is also one of the reasons why Iran thought that let's launch an attack. Anyway, nobody is going to be harmed, no casualties will happen. They are going to counter all the missiles and drones. And at the same time, it sends a message that look, we are not going to hold back anymore. We are not going to fight a shadow war anymore. We are going to go all out. Now, in this scenario, if a direct conflict happens, and I would always hope it doesn't, but if a direct conflict happens, in that scenario, Israeli defense system is way stronger than Iran's right now. Iran, in this particular scenario, currently is not in a position to fight a direct war with Israel, because there is a huge difference between the capabilities of Iran and Israel in the current scenario. But at least, I mean, for the first time, we saw that Iran actually took an extra step and went ahead. Now, coming to nuclear fusion. But before that, again, if you have any doubts, anything with regard to nuclear fission. Didn't understand nuclear fission. So the process, what I'm saying is that you have uranium 235 isotope of uranium. You bombard a nucleus, a neutron towards it. Neutron gets absorbed. It becomes uranium 236, which is very unstable. It breaks into two parts and releases a lot of energy while breaking. And that is the energy of nuclear fission. What is IAEA? It is International Atomic Energy Agency. Hmm. So all good then. How will they enrich uranium? The enrichment process is very similar to the centrifugation process. How centrifugation works, if you have seen how milk and fat would be separated out, so it's a very similar process. Does Israel possess nuclear weapons? Yes, Israel does have nuclear weapons. Why there's a difference in the process of nuclear fission? The difference in the process. See, it is something which is possible only with uranium 235, and something that we can create, conditions that we can create. And the kind of energy that we get is huge. I mean, compared to that, radioactivity is nothing. Radioactivity is nothing as compared to the kind of energy that you get out of nuclear fission. Does India also make weapon grade uranium? India has weapon grade uranium already. We have done all our work in 1960s and 70s itself, and we know the process, we know how to do it, and we do have weapon grade uranium and plutonium as well. This process leads to continuous formation of krypton and barium. Yes, it does. We bombard neutron. No, we bombard. Bombarding meaning that we are taking this neutron and we are throwing it towards uranium 235. Half-life concept, we'll discuss that towards the end of this chapter, not now. How when increasing from 5% to more, uranium-235 becomes weapon grade. See, the instability in that uranium increases, and there are a lot of internal factors of weak forces also that make it very unstable. So that actually is what happens. Energy multiplied cubically, yes, that's the case. From 1 to 3 to 9 to 27 and so on. So that's true. Neutron of uranium bombarded? No, neutron is bombarded. And neutron is neutron. See, electrons, protons, and neutrons, their properties do not change depending on what element it is. They are all the same. Their configuration is different, their structures are different. Give me just 2 minutes. I need to drink water. I forgot my bottle. Hmm. Yeah. So let's move to the next topic. And the next topic is nuclear fusion. Now, just as we discussed about fission, can you tell me the dictionary meaning of fusion? What do we mean by fusion? Yeah, to combine, to join, correct? So, fusion means what? Fusion means to join or to combine. So, this is what is happening in nuclear fusion, that there are two nuclei that are combining together. In nuclear fission, they were breaking. This time they are combining. So, occurs when two lightweight nuclear fuels combined and they form nucleus of a heavier element. So if you see, you have two nuclei of hydrogen, deuterium and tritium. They are combining together and they are forming helium. And while forming helium, they are releasing huge amount of energy. So in nuclear fission also and in nuclear fusion also, we are getting a lot of energy. We see a release of a lot of energy. And how exactly this happens? If you look at these reactions, this is what happens inside the sun. This is what happens inside the sun. And we know that sun is a huge source of energy. It is basically driving the energy in this solar system. All the sunlight that we get, all the heat and light that we get, which becomes the source of all the energy, or a huge amount of energy on the earth also, it all comes from where? Inside the sun, core of the sun, where you have nuclear fusion, where you see that nuclear fusion is happening. So these are the reactions that happen inside the sun, where we see that two hydrogen nuclei, they join together to form the heavier hydrogen, that is deuterium. And this deuterium further keeps on combining with more of hydrogen to form helium 3. Now this helium 3 is unstable. This helium 3 is unstable, so it keeps on reacting further with more of helium 3 and ultimately forms helium 4, which is stable. Helium 4, which is stable. So what we basically are looking at is that hydrogen has converted into helium while releasing a lot of energy. So so that's why we see that there are extreme amount of energy that can be produced with the help of nuclear fusion. And the kind of energy, the amount of energy that is produced by nuclear fusion is way more than even nuclear fission. Nuclear fission produces huge amount of energy, no doubt about it. But compared to that, the amount of energy that nuclear fusion produces is even more. It's very high. So that's why nuclear fusion is the source, you can say, of the entire solar system itself. So that's the amount of energy that nuclear fusion packs. Now, when it comes to nuclear fusion, for nuclear fusion to occur, it is necessary to bring two nuclei so close that nuclear forces between them become active and they make them fuse together. Now, what happens is that to produce the conditions, which are required for nuclear fusion to occur, we need very specific conditions. And unless you have these specific conditions, nuclear fusion is not possible. Getting nuclear fission to work is a lot easier. Getting nuclear fusion to work is a lot more difficult. And that's why there are very specific conditions under which nuclear fusion is possible. So, what are these conditions? Conditions for nuclear fusion. What are the conditions for nuclear fusion? One, extremely high temperature. Extremely high temperature, extremely high pressure, extremely strong magnetic field. Now, all these conditions are there at the center of the sun and or at the center of any star. And that is the reason why the sun has so much of energy, why any star has so much of energy, all because of all these conditions which are perfectly placed for nuclear fusion to occur. And that's why we see that any sun, or I mean our sun or any star, undergoes nuclear fusion at its center and releases a lot of energy. Can we do it artificially? The answer is yes. It is possible to do the same artificially, but doing that is not easy. Getting these conditions, creating these conditions is not an easy job. There are two approaches that we use. To make these conditions, and this is called as confinement approaches. So, what do we mean by confinement approaches? This is basically conditions creating conditions to make nuclear fusion possible. Creating conditions to make nuclear fusion possible. So these are called as confinement approaches. Now there are two confinement approaches that are used. One is called as magnetic confinement. The other one is called as inertial confinement. Now, when it comes to magnetic confinement, it uses strong magnetic field to confine the plasma to create the conditions needed for fusion energy production by using electrical conductivity of the plasma to contain it with the magnetic field. Now, what we do here, we create magnetic field in toroidal shape. So, what we create is toroidal shaped magnetic field. Toroidal shaped magnetic field. Do you know what is toroidal shaped? What is toroidal shape? Mm, some of you know, correct? Some of you don't. Okay. Do you recognize this shape? The shape of a donut or shape of a medu vada? Do you recognize that shape? That shape is basically the toroidal shape. This is the toroidal shape. So now what do we do here? This basically is what we create. This is the kind of magnetic field that we create. So something like this. So this basically, this is the toroidal shaped magnetic field. All right, this is the toroidal shaped magnetic field that we are creating all across the plasma, all across the middle region where the reactions can happen. All right, so this is basically what we do. So toroidal shaped magnetic field has to be created, and magnetic confinement is how we do it. So in magnetic confinement, magnetic field is being used. That's why magnetic confinement. We are creating the conditions with the help of very strong toroidal shaped magnetic field. Now, the other one is inertial confinement. Now, inertial confinement basically is where we are making the use of powerful lasers or ion beams. So what we do is we use lasers from both the sides, and with the help of lasers, we provide enough energy so that these particles can come together. These particles can combine together. So for that, from both the sides, we will be pushing these particles with the help of the energy of the lasers. The energy of the lasers will do that. Now here, when it comes to the energy of the lasers, there has been very important breakthrough, very important breakthrough that has been achieved with the help of inertial confinement. The Lawrence Livermore National Laboratory, which is there in the US, they have been able to produce more energy from fusion than the laser energy used to drive it. Now, what do we mean? So, when we say breakthrough, that there are two articles that you see, one of December 2022 and then of August 2023, where we are talking about some kind of breakthrough in nuclear fusion. Now, this breakthrough is very important because for the first time, we have been able to produce more energy, generate more energy from nuclear fusion than the energy that was consumed in the operation. Understand why this is very important. Because if let's say you are using 100 joules of energy to get 50 joules of energy, does it make any commercial sense? You are using more energy and getting less energy. What's the point? There's no point in doing that, right? So energy will only be viable for you or commercially viable for us when you are getting more energy from you by using less energy. Until now, what was happening? We are using or we are wasting more energy with the lasers and getting lesser energy. Doesn't make sense. But for the first time, they got this breakthrough. They got this breakthrough and they used lasers to fuse two light atoms into single one, releasing 3.15 megajoules of energy from 2.05 megajoules of energy, which is enough to boil some kettles of water. All right. So only this much amount of extra energy we got that we can boil some water, we can boil some kettles of water. That's it. But for the first time, at least we are in the green. We are positive. We have generated more energy than we have consumed. So that's why it is a very important breakthrough. And that's why many of the scientists started saying that, okay, now nuclear fusion is just 20 years away. They started saying that nuclear energy is just 20 years away. And this is something that we have been hearing for the last 40 odd years, that nuclear fusion is just 20 years away. So 20 has not become 19 in the last 40-45 years. But look, making a meme is easy. Actually, getting energy out of nuclear fusion is not. So we can joke around as much as we want, but this is the reality that getting energy out of nuclear fusion is not an easy job. So even if they have this breakthrough now, that they have been able to get more energy out of the entire operation, at least we have something in the positive direction, and we can expect that in coming future we might see something better with nuclear fusion. So this is where we have seen that inertial confinement has been used. Inertial confinement has been used, which is very, very important. Now, there are certain other developments also. One development is of International Thermonuclear Experimental Reactor, ITER. Now, this is something which is under construction and is slated to be completed by 2035. It might become operational by 2035 in France, under construction in France. Now, this ITER is a large scale scientific experiment that aims to demonstrate that it is possible to produce commercial energy from fusion. And with the help of what? With the help of magnetic confinement. With the help of magnetic confinement, we are running an experiment where we want to produce nuclear fusion based energy, where we want to make nuclear fusion commercially viable. Now, in this context, we see that initially it was started by the former Soviet Union, the US, European Union, and Japan. And later on, India, China, and South Korea, these three countries, we have also become a part of the ITER. And some of the components are being made by all of these countries. For example, a very important component is the cryostat in the ITER, which actually has been made in India or made by India. So that's why we see that uh, there are contributors, and all these countries and organizations and unions, they are actually contributing towards ITER. Similarly, what we see is that there is this news last year in the news in October, then in December also. First plasma fired up at world's largest fusion reactor. This is Japan's JT60SA tokamak. Tokamak. Tokamak basically is this central figure that you see. This is the tokamak. Tokamak largely is the toroidal shaped instrument that we were talking about. So that basically is what the fusion is being carried in. And you can say that this JT60SA is a miniature version of ITER. All right, this basically can be considered a mini version of ITER, where we are trying to make fusion possible. We are trying to generate electricity out of nuclear fusion. So that is basically where we are with regard to this. Now, understand nuclear fusion, because nuclear fusion comes with a lot of advantages over other energy sources, over nuclear fission as well, over renewable energy also. We see that nuclear fusion holds a lot of advantages. First, we get abundant amount of energy. Our sun is an example, the kind of energy that nuclear fusion can produce. Sustainability, it can be used for a very long time because it is hydrogen based. All right, it is hydrogen based. So because it is hydrogen based, it means that it can be used for a very long time. Same goes for the third point also, that no carbon dioxide, because it is hydrogen based, right? Because it is hydrogen based. So that is basically what we see here. And again, no long lived radioactive waste, which is an issue with nuclear fission. All right, this is an issue with nuclear fission because the radioactive wastes that are generated by nuclear fission, they last for very long, thousands of years. They can last for thousands of years. Just imagine this, the waste that is generated, and the waste, if let's say any leakage happens, any accident happens, it can be there in the environment for more than thousands of years. Plutonium, for example, for 20,000 years. Just imagine this. So, and that is not the problem with nuclear fusion, because nuclear fusion, the radioactive waste that is produced by nuclear fusion, it lasts for seconds. It lasts for seconds. For example, tritium water. tritium water, lasts some seconds. So that's why the kind of waste that is being produced, it is lasting for seconds and not thousands of years. Then limited risk of proliferation. Now proliferation basically is expansion, or when you are weaponizing it. So in a manner, in simple terms, you can say weaponization. So limited risk of weaponization. Now, why are we saying this? Again, when it comes to nuclear fission, the same process, enrichment process we discussed, the same enrichment process, you do more enrichment, and instead of producing electricity, you start making atom bombs, right? But that's not the case in case of nuclear fusion. Even if you have to make fusion based bomb, the process will be entirely different. The same process can't be used. Then no risk of meltdown, which was the case with nuclear fission. In case of nuclear fusion, there is no problem of meltdown. It can very easily, because the conditions that are required for making nuclear fusion work are very extreme conditions. And unless you have these extreme conditions, you cannot look at a risk of meltdown. And the cost factor being that once we start using it, it will drastically bring down the cost in the future. Right now we can't say that, but once we crack the code, once we understand how to use it, then we'll see that the cost will also be brought down. So that's why nuclear fusion actually will hold a lot of advantages altogether. Read this question, a very simple question on ITER. It was asked in your 2020, 2016 paper. I'm launching the poll also for you. It's a very, very easy question. India is an important member of the International Thermonuclear Experimental Reactor. If this experiment succeeds, what is the immediate advantage for India? Please mark your answers. So 65% of you have marked D, which is the correct answer. But there are some of you who are confused. So let me just discuss this with you. See, we are talking about ITER. What is the context in which we have talked about ITER? Nuclear fusion. Look at option A. It can use thorium in place of uranium. Uranium, thorium, nothing to do with fusion. Fusion is hydrogen based. It can attain a global role in satellite navigation. Where did we discuss about satellite navigation? It can drastically improve the efficiency of fission reactors. Is it related to fission? It's not. We are left with only one option, that is D. It can build fusion reactors for power generation in the future. That is what we want. This is what ITER is all about. So that's the correct answer will be D. Very simple question. So let's stop the class here. We have nuclear reactors and India's nuclear program that we'll discuss in the next class. But before that, if you have any questions, please let me know. Rashmi, whatever be the problem, if you can just send an email to me also, I'll try to connect you with the team, so that if they can solve your problem. I don't know what the problem is, so I can't comment on it. What ITER does. So see, ITER is nothing but an experimental reactor that we are building, right? And once the reactor is completed, then we will be able to produce nuclear fusion based on magnetic confinement. What is magnetic confinement? Magnetic confinement is when we have very strong magnetic field all across the charged particles where the reactions are occurring. just like the sun. Sun has very strong magnetic field all across. So that helps in nuclear fusion. What is the meaning of plasma? Plasma is nothing but, let's say, charged particles. Simple words, you can say charged particles. How enrichment is done? It's just like centrifugation, where the process that we use to separate fat from milk, the same process. What is the practical use of fusion reactors? Electricity. We want to generate electricity from fusion. Nuclear fission occurs for any element which are above 83? No. Nuclear fission happens, the only naturally fissile material, the only material which is naturally capable of undergoing fission is uranium 235. Apart from uranium 235, nuclear fission doesn't happen in any other element. I'll write it there itself so that it will be there in your notes. Hmm. Uranium 235 is the only element capable of undergoing fission naturally. So, so that's why we say that it is naturally fissile. So anything that can undergo fission is called as fissile. So naturally fissile is only uranium 235. As uranium 235 is limited, how will it increase? The same process, enrichment. Critical mass is that after which it becomes atom bomb, and if the mass kept below, electricity is generated. Here, mass is mass of element or mass of the nucleus, not mass of the element, rather mass of the nucleus. Is making handwritten notes beneficial or taking its print? See, it actually depends from person to person. I mean, if you ask me personally, I would always write. I am a person who likes to write and understands thing only when I write. So I have this process, but many of my other friends who have qualified also, they had a different habit. They would just take the notes. I mean, they would just take the printouts and read from there. So it really depends from person to person. Disadvantage of nuclear fusion, I mean, right now technologically it is not viable. That is the problem. Hydrogen bomb versus atom bomb. Hydrogen bomb is basically fusion based, largely fusion based, and atom bomb is fission based. That's the basic difference. What is written after naturally fissile, FISSILE, fissile. Artificial fission, Kunal will discuss about this tomorrow. Hmm. Mains questions we'll discuss tomorrow after this class. I mean, this chapter is completed. I'll discuss the questions with you. Right. So I think we are done. So we'll continue from here. We'll discuss about the nuclear reactors and we'll discuss about India's nuclear program and the various aspects of applications of nuclear energy in tomorrow's class. All right. So till then, please go back and revise. What we discussed today is a complex portion, so it will need your your revision, and study this. Come back if you have any doubts. We'll clear it tomorrow. Thank you.